Okay, with that said, I think we're going to start perhaps one of the most exciting topics. We've kind of been building up to it in this class, the out-of-order execution. This is a way of executing instructions out of their original program sequence. And it's a very influential way. It's been used in essentially all computers today. Even though some people started saying that we're not going to use sophisticated hardware techniques to actually execute instructions, we're going to punt all of the difficult things to the compiler. They've all come to use out-of-order execution today. After 10 years, 20 years, they figure out, no, you have to use hardware to actually accelerate instruction processing by doing things out of order. So you'll see the importance of this into the future also. We'll cover the basics. There are a lot of optimizations that build on what we cover. Unfortunately, we'll not be able to cover all of those optimizations clearly. Today's out-of-order execution engines, like what's in my pocket, for example, or what's here, are very, very sophisticated engines. And I will show you a picture of, I guess, kind of what's in my pocket, somewhat reverse engineered, as the very last slide of this lecture. Does that sound good? Okay, cool. Okay, so this is where we are. Basically, we've covered a lot of pipelining, precise exceptions. Yesterday, we set up for today, we talked about register renaming the registers from the architectural register space to a microarchitectural namespace, which we called reorder buffer yesterday. Today, we're going to use that concept. But today, we're going to finish out-of-order execution, hopefully. And I will release a premiere of load store handling. Unfortunately, we don't have time to really cover load store handling. But for your own benefit, you can watch that and see. That's really the most sophisticated part of the machine today, how to handle loads and stores. It used a lot of content addressable memory. You got introduced to content addressable memories yesterday. Unfortunately, that part is very difficult to eliminate content addressable memories from. Okay, these are your readings. I think you've seen a lot of these, but except for this optional one. This optional one covers a state-of-the-art processor in 1999. A lot of the principles remain the same today. Today, there are a lot more optimizations. And next week, we're going to cover branch prediction, which is essentially how to keep the pipeline full in the presence of conditional branches. And this paper covers a lot of interesting ideas in 1990s, let's say. Of course, we're going to look at much more advanced ideas this week. Okay, this is where we what we built up to yesterday. We built an in-order pipeline with reorder buffer with multi-cycle execution units, as you can see. And we did that by using a reorder buffer. We did the instruction reordering precise exception using a reorder buffer. I'll go through this just to jog your memory. But basically, in a pipeline like this, in the decode stage, the instruction accesses the register file and the reorder buffer, allocates an entry in the reorder buffer, and you check if the instruction can execute, meaning if the source registers are ready. If that's the case, you dispatch the instruction into the functional unit. Okay, if one of the source registers is not ready for whatever reason, you cannot dispatch the instruction. That's a non-ready instruction. That basically stops the pipeline. And the instructions can complete out of order, which is good. And when they complete, they write their results to the reorder buffer first, which is microarchitectural. They don't update the architectural state immediately. The architectural state gets updated in program order when the oldest instruction doesn't have any exceptions and it's completed. It writes, there's some control logic that writes the result to the architectural register file or memory. Otherwise, if there's a problem with the instruction, the control logic flushes the pipeline and starts from the exception handler, or if you're handling an interrupt at that point in time. Basically, this is an in-order dispatch machine. Dispatching means sending instructions to the functional unit. An out-of-order completion machine, you complete the instructions out of order. And you retire instructions still in order, in program order, as specified by the sequential semantics of the program, right? This is also called an in-order execution machine because I like in-order dispatch better because you're really dispatching an instruction to the functional unit in program order, but you're also starting the execution of instructions in program order. Basically, you don't start the execution of instructions out of the program order, out of sequence, if you will. Today, we're going to start the execution of instructions in functional units out of order. Okay? Okay, so let's move on. So this is what we've covered. We basically said that register renaming eliminates the write after read and write after write dependencies, which are not real. These exist because there are not enough names in your register file, in the architectural register file. And we're really, the only dependencies that we really need to deal with are flow dependencies. So in order to deal with flow dependencies, what you really need is to make sure that the dependent instruction gets connected to the producer. So you can think of this as this instruction is producing the value of R3, and this instruction is consuming the value of R3. You really need to connect the producer to the consumer. When the consumer comes into the machine, the consumer needs to know where to get its value from. Okay? Here, you can get rid of these dependencies because they're not real dependencies. You can rename this R1 to something else, R1000, let's say, or reorder buffer something, some reorder buffer entry number. As a result, this value has nothing to do with this value, which makes sense, right? We've discussed this multiple times. And that's true for this output dependence also. Basically, we have seen yesterday, again, that the output and anti-dependencies exist due to lack of register IDs or names in the ISA, instruction set architecture. And they're not real dependencies because the same register refers to values that have nothing to do with each other. Meaning there's no producer-consumer relationship between these two instructions. They just happen to be writing to the same register that is allocated to the value that they're supposed to produce. But from a communication perspective between instructions, there's nothing between these two instructions, right? They just happen to collide in the namespace, if you will. And basically, we eliminated this problem, this collision in the namespace, by renaming the architectural register ID to the reorder buffer entry yesterday. And you remember the illustration we went through. We're going to go through a very similar illustration today. Basically, we said that register ID, the architectural register, is renamed to a reorder buffer entry ID. You can also think of this as architectural register ID being renamed to a physical register ID. And after renaming, reorder buffer entry ID is used to refer to the register. Basically, you don't need to hold on to the architectural register ID until you update the architectural register state at the end of the machine. And we will see that. And the benefit of this is now this eliminates anti and output dependencies so that when you're dispatching an instruction in a multi-cycle execute machine early on, you don't need to stall. So basically, you can dispatch instructions by eliminating anti and output dependencies. You don't need to stall at this point. Okay? So as long as they are ready, of course, as long as these instructions are ready to go. Okay. And this also gives the illusion that there are a large number of registers. Because of ISA, you have limited number of architectural registers because of the instruction encoding is limited. But now you expand the register space by renaming that architectural register space to a much larger physical register space or microarchitectural register space called the reorder buffer yesterday. But you will see today that this reorder buffer is actually just one place where you can rename architectural registers. You really need a larger namespace, and you will need to provide space for it. It doesn't have to be the reorder buffer. And we will see that today. We will introduce the concept of reservation stations, and we will basically rename the registers to the reservation station IDs. It could be any namespace, actually. In existing processors, it's the physical register file, and we will also build up to the physical register file in a little bit. Okay, but yesterday we saw that you rename the architectural register ID to the reorder buffer entry ID. And this is how we did it. I'm not going to go through this example again, but remember that if an instruction is writing to R0, for example, it sets the val bit of the R0 to 0. The value becomes not useful for future instructions at that point, but you also, the instruction, when it's being decoded, sets the tag to the reorder buffer entry ID of the instruction, because every instruction gets allocated a reorder buffer entry. So this tag at that point refers to the renamed register. So register 0 is renamed to this tag, which happens to be the reorder buffer entry of the instruction that's producing that register. And we said that yesterday, if all of the instructions in the machine are writing to a particular register, say register 3, there may be 16 definitions of R3 in this particular reorder buffer because there are 16 entries, as you can see. As a result, the register may be renamed 16 times. And the later instructions will get the correct value because instructions are being decoded in order. They will see the tag that is updated by the latest instruction that's writing to R3. That's the beauty of the in-order decode, okay? So every instruction that's going to source R3 will get the correct definition of R3 or correct location in the reorder buffer that's going to produce the R3 value that this instruction is supposed to take because of the in-order renaming that happens in the beginning or in-order decode. So basically, this is the new name. You can think of this tag as the new name of the architectural register. Makes sense, right? And internally in the machine, you don't need to know about R0, R1, R3, R4 anymore You just care about this tag. And this tag can be used to communicate the readiness of a value. So for example, if an instruction that's producing R5 has a tag 16, reorder buffer entry, well, it doesn't exist over here. Let's say tag 14, reorder buffer entry 14. It can say, I'm producing reorder buffer entry 14. Anybody who wants reorder buffer entry 14, compare your tag to it. If it's what you need, then get the value that I'm sending to you. So this is how we're going to accomplish communication, basically. No more architectural register names. And you're going to see that soon. Okay, and this is also one slide we covered yesterday. We're going to look back to this today also. But basically, you can think of this as a renaming table, and Intel calls this the register alias table. Essentially, you have a bunch of architectural registers. Some of them are in the architectural register file, and some of them are in the reorder buffer. And you basically have pointers from this register alias table to the definitions of the registers that you're supposed to get. Okay? So this is very similar, actually. This picture is very, very similar to what I've shown, except Intel has decoupled, taken this tag, and only the tag is over here, basically. So what I have done is basically tag and values together and val bits, and then a separate reorder buffer. But Intel has pulled out the tags over here. And we will see the reason for this also later on. But it's essentially the same thing. These two pictures are essentially the same thing. The values happen to be separated over here in the retirement register file that Intel calls. Okay, we'll get back to this picture. And we'll get back to a more advanced picture also. Any questions? This is kind of a relatively short review, but also I wanted to motivate some things that we're going to discuss today also. So now we're going to talk about out-of-order execution, which is really dynamic instruction scheduling. This is also called dynamic instruction scheduling because the scheduling of the instructions is done by the compiler, right? When you get the program. Compiler does some reordering of the instructions, etc. And that's a static schedule. Now we're going to violate that schedule internally to decide which instructions should dispatch to the functional unit in which order. So let's take a look at this pipeline that we have looked at earlier. Basically, remember, dispatch is the act of sending an instruction to a functional unit. I ignored the reorder buffer allocation over here, but I will have it over here. Later, I'm going to eliminate reorder buffer to explain things more simply, but we're going to reconstruct it again, hopefully. Basically, we used renaming with a reorder buffer to eliminate stalls due to false dependencies. Basically, if you do renaming, when you get a false dependence, you don't need to stall because you eliminated that dependence, right? Now, the problem still remains that if an instruction is not ready, if there's an instruction that's being decoded over here, and if it doesn't have the values that it needs, or any one of the values that it needs, unfortunately, it cannot go and get dispatched. As a result, no other later instruction can get dispatched. So basically, an instruction stalls if it's not ready. So we're going to fix this problem today. And I'm going to use or abuse the example that I used earlier. So if you look at this instruction, this tram over here, it's long latency for whatever reason. I don't care if it is an exception. Maybe it's long latency because it's doing something important, right? Unfortunately, this instruction stalls the pipeline. There's another independent instruction. It's going somewhere else. Let's say it's using some other functional unit. It's going to use some other functional unit. Unfortunately, it cannot enter the pipeline because there's this long latency instruction stalling the pipeline. I think it's very similar to this concept. And then there are other instructions. So one way we could have enabled this instruction to enter the pipeline is bypass it, right? Maybe put this instruction somewhere else, right? And we're going to do that essentially. Of course, it's much harder to do in the tram lines, but unless you have parallel tram lines or somewhere to buffer. So if you have somewhere to buffer this tram, like a bigger area, then other trams can bypass it, right? And that's the idea that we're going to do today. Okay, so you can see the consequences of stalling. People start walking as opposed to taking the tram. But finally, the independent instruction is dispatched and it's executing over here. But we don't want it to wait. If we know that an instruction can actually go ahead earlier than an older instruction, we should enable that instruction to go ahead so that we can get high performance, right? That's the idea. Okay, so that's the problem we're going to solve today, basically. So basically, can we do better? Can we do better than what we have built up to yesterday? And the idea will be, yes, how can we do better? Before we discuss this, I'm going to talk about some alternative ways. So let's take a look at this example code. Both of these codes are actually very similar to each other. If you're observant, you will see that the last 4 instructions are exactly the same. Add instruction is dependent on the multiply here. Add instruction is dependent on the load instruction here. And all of these 3 blue instructions are independent of the add or the load. But basically, when you fetch the first add, it stalls the whole pipeline because it's waiting for this R3 to be available, right? Assuming that multiply takes a long time and load takes a long time, okay? If it takes one cycle, it's not going to stall the pipeline because, but unfortunately, the pipeline may be long, so it depends on when you actually generate the value. So basically, add cannot dispatch because its source register is unavailable because it's dependent on the multiply or the load. But later instructions also cannot get dispatched. Basically, blue instructions, these poor blue instructions have nothing to do. They're not waiting for the result of the add or the multiply, but unfortunately, they cannot get dispatched because there's nowhere to put them, let's say, or nowhere to put the add. So we're going to fix that problem, basically. So I should also mention that these two code portions are different in the sense that load latency is actually very different potentially, right? Load latency is quite variable. It's actually unknown until runtime. And this causes more problems. So multiply latency may be known. It may be all multiplies take 4 cycles or 8 cycles. But load latency will depend on where you will service the load from. Will it come from the L1 cache, L2 cache, L3 cache, main memory? Will it get a page fault, as we will see? But we will see all of those later on, starting with lecture 20 or so. So hold on to that. So loads are going to cause us a lot more headache, basically, in the future. That's why we're not going to deal with loads today, at least. We're going to deal with an example of multiplies. So basically, start thinking about this, basically. This is easier for the compiler to potentially try to schedule and avoid this stall. It's still not that easy, but compiler's job is a lot harder over here, basically, because compiler has no idea potentially that this load is going to hit or miss in the cache, okay? So whenever you have memory access, things become a whole lot worse, let's say. So that's why I think a big focus today in modern systems is to figure out how to deal with memory in a much better way. Okay, so let's talk about preventing these dispatch stalls. You have this instruction that's not ready, add. It's not ready because it's dependent on a prior instruction that doesn't produce its value yet. How do we prevent these stalls? So basically, the problem is really in-order dispatch or in-order scheduling or in-order execution. The solution that we're going to pursue is really out-of-order dispatch. Basically, figure out some way of dispatching these instructions out of order. Of course, you need to make sure that everything still works correctly. That's why we're going to add a lot of hardware. But we've seen the basic idea before, actually. If you remember the data flow says that fire an instruction only when its inputs are ready. Right? It's essentially the same thing. Right? Start executing an instruction when its inputs are ready. In fact, start fetching the instruction when its inputs are ready. So data flow takes this concept to a next level. So what we're going to do in this lecture is build an internal data flow engine inside a control flow machine, meaning from the programmer's perspective, it's a von Neumann machine. But from the microarchitecture perspective, it's actually going to produce a data flow graph of a program. And then, and actually, I'm going to go through an example where I will show you that by just looking at the internals of the state of the machine, you can reverse engineer the data flow graph of the program that's executing. I think that's very beautiful, basically. And we're going to combine these two concepts. But we're not going to make life harder for the programmer, telling the programmer you're going to program in data flow. We're not going to do that. Programmer is still going to program using sequential instruction streams. Okay, basically, we will use similar principles as data flow, but not exposed in the ISA. That's the same thing I said in a different way. But we've also seen any other ways to prevent dispatch stalls. Anybody name some? We've seen 3 ways of actually preventing dispatch stalls, without calling them dispatch stalls, of course. Anybody? Yes? So data forwarding helps, yes. It didn't come the first way. Okay, think about it. Maybe some other things? So I've given you this one, right? Compile time, instruction scheduling, reordering. So if the compiler is able to schedule instructions such that the value of an instruction is always ready when the instruction starts getting into the pipeline, that could work, right? But this is a very tough problem. People have tried to actually work on this problem for decades and decades. It's still not enough. But this is still possible to do in some cases, especially if the code is regular. Maybe related to data forwarding, you can predict the values. This is a tough problem also. Okay, if you can actually predict the value, for example, if you go back over here, this picture. So here, for example, the compiler could have reordered these blue instructions earlier than the add and tolerated the latency of the multiply, right, potentially. So that's the compile time reordering, if the compiler can do that. Usually there's not enough parallelism that the compiler can expose. Value prediction says, Don't do that, but predict the value of R3 that's happening here. Maybe you don't have the value of multiply. Okay, predict that it's 0. Is that a good idea? How do you predict it? Not so easy, basically. Value prediction doesn't always work. But we've seen one idea that really works very well. Anybody? Your last chance. Really works very well under specific circumstances. Fine-grained multi-threading. Basically, if you do fine-grained multi-threading, there's no problem. There's no dispatch stall. If you have enough threads, all of the instructions are independent. They're from different threads, but basically the pipeline never stalls, right? That's beautiful. But this requires you to have enough threads. And also, if you really care about the performance of a single thread, this is useless for you, right? If your goal is to really improve the performance of a single thread, you cannot basically resort to multi-threading, unfortunately. Fine-grained multi-threading, at least. So we've seen actually all these ways. The first two can help the performance of a single thread, but usually they're not very well applicable. The third one is very useful when you have lots of threads, but it's actually hurtful when you have a single thread. It's actually because you're fetching from a one thread every n cycles, where n is the number of pipeline stages that you have. Okay, so that's why out-of-order execution has been very successful, basically. None of these methods work. So the idea of out-of-order execution is very simple. I've kind of hinted at this. Move the non-ready instructions out of the way of the independent ones. Basically, add some hardware buffers. And if an instruction is not ready, no problem. Move it somewhere else. In fact, what we're going to do is do it more methodically. Every instruction is going to go into a buffer first. And then we're going to schedule the instructions out of those buffers. Make sense? These will be called reservation stations. And we're going to examine which instructions are ready and which instructions are not ready. And then we're going to schedule the instructions or dispatch the instructions from these buffers. Okay? That's the beauty. So you can think of, at the beginning of the pipeline, we're going to add a big buffer called reservation stations. And all of the instructions are going to get buffered there until they're ready to execute. You can also think of this as rest areas for non-ready instructions or reservation stations. If you're driving on the highway, when you need to stop, you don't stop in the middle of the highway, right? If you do that, you may have a lot of trouble with people behind you. But that's what we were doing in the pipeline earlier. Somebody needs to stop. This multiply instruction is taking a long time. He needs to go to the restroom or whatever. Stops right in the middle of the highway, and everybody else gets backed up. Well, go to the rest area, right? Wait over there. So that's the idea, basically. But again, we're going to be more methodical. Every instruction is going to go there because otherwise it's a bit harder to deal with some things, but we're not going to go into that. Basically, in this resting area, waiting area, instructions are going to monitor the source values. Basically, is my value ready? Is the register that I'm sourcing ready? And if both of them are ready, if it's a binary, if it has two registers, then the instruction becomes ready. When all source values of an instruction are available, we fire in data flow terms or dispatch the instruction to the execution unit. Sounds beautiful now, right? So basically, instructions are dispatched in data flow order, not control flow order. So that's the key realization. We can dispatch instructions in data flow order. So the big benefit over here is latency tolerance, meaning that if an instruction is taking a long time, it's not going to stall the pipeline. Independent instructions can execute and complete in the presence of a long latency operation, which could be a multiply, as I showed you earlier, which could be a load, as I showed you earlier, which could be anything, actually. As long as it takes more than one cycle, you can tolerate that latency if this mechanism is able to find independent instructions in the program. And people have shown that actually there's a lot of independence in the program. There's a lot of instruction level parallelism. If you look at a larger window of a program, this instruction level parallelism may not be easy for the compiler to discover. That's why hardware is more easy to discover, because compiler may not be able to safely determine which instructions can be executed before which other ones. Because if it moves the code from one place to another place, it's really potentially violating some semantics in the program, right? Here, we're not violating semantics in the program. We're just deciding which one should execute early or late. We're not moving code anywhere. The code is exactly what the compiler produced, and the compiler can say, I'm not going to change the code that the programmer dictated, right? Okay. Everything's clear? Okay, so basically, let's take a look at this pictorially. This is the in-order dispatch machine with precise exceptions that we've built. This is the code that I'm showing you. Red means dependent. So this is dependent on the multiply. This is dependent on the multiply. But the blue ones are independent, as you can see. Here in this pipeline, you execute the multiply. Multiply takes 4 cycles in this particular case, as you can see. When you decode the second add, you stall the pipeline, right? And the next instruction stalls, everybody stalls after that. With out-of-order dispatch and precise exceptions, instead of stalling the pipeline in the first add, you put it into an area where it waits, and then you keep filling the pipeline, and you figure out that this instruction can execute, right? It executes, generates its results, writes into the reorder buffer, and then the next instruction can also execute, but this instruction also goes to waiting. So you can see that by just looking at this piece of code, you can reduce 16 cycles of execution time to only 12 cycles. And that's a lot, actually. That's 25%, right? Improvement. And in large pieces of code, empirically, people have shown that out-of-order execution actually gains 30 to 50% performance improvement compared to a very aggressive in-order dispatch machine, sometimes even higher. My PhD thesis, for example, shows that it's much higher. Okay. So, what do we need to enable out-of-order execution? So there are 4 things that you need to enable. One is you need to make sure that the correct data value semantics are obeyed, meaning the consumer of a value needs to be linked to the producer so that the consumer gets the correct value or a correct definition of a register. And this is done via register renaming, as we will see. Then you need to buffer the instructions until they're ready to execute, because you need to prevent the dispatch stalls and you need to provide some place, hardware, to keep these instructions. While the instructions are being buffered, they need to keep track of the readiness of their source values, as we have discussed, and we're going to talk about that a little bit more. And then when all the source values of an instruction are actually ready, we need to dispatch the instruction to the functional unit. So these 4 things are necessary. And when the instruction actually produces its value, it's actually going to broadcast the tag such that the consumers can get the value after it executes. So the first one is accomplished. Linking of the consumer to the producer accomplished using register renaming that we have seen. We associate a tag with each data value, and we're going to see that more today. Buffering of instructions until they're ready is accomplished using reservation stations. You insert instructions into reservation stations after renaming. It has a historical name, unfortunately. It's called reservation stations. Some processors call these issue queues. I kind of like reservation station better. It's sort of like a resting area, a resting station, if you will. How do the instructions keep track of the readiness of the source values? Basically, an instruction that produces a value broadcasts a tag or the name of the register when the value is produced. Instructions that are waiting for that tag compare their source tags to the broadcast tag. If there's a match, that means that the instruction is waiting for that value. Then the source value of the instruction becomes ready. Okay? And when both source values of an instruction are ready, or when all source values, because some instructions wait for 1 value, some instructions wait for 2, in rare cases 3 values. But if all values are ready, then the instruction wakes up. And if multiple instructions are awake, there needs to be some logic to select one instruction to send to the functional unit. So there needs to be more arbitration because multiple instructions can wake up at the same time, right? Make up meaning ready, become ready. So there's all of their sources are ready. Okay, so that's the idea basically. Does this sound good? Now we're going to implement this in hardware, and this is clearly going to cost us something. It's not going to come for free. We've had register renaming, so that's not going to cost us, but everything else over here is going to cost us. And the cost is a lot. That's why people have optimized this over the course of multiple decades. So I will also mention that this register renaming, this algorithm is one way of doing out-of-order execution. It's the dominant way today. It was invented by Robert Tomasula, who was a chief architect at IBM. In IBM 36091's floating point units. And remember, if you remember, I mentioned this as an example out-of-order machine. And you can read actually this beautiful algorithm that we're going to go over in this paper. The major difference today is IBM 36091 did not have precise exceptions. And as I mentioned, it was not successful because of that. So this was implemented in the 1960s. In fact, when these folks, these engineers wanted to implement it, they said, it's too costly to support precise exceptions. So can we do imprecise exceptions? So they went all the way to the IBM's boss, big boss, and they reluctantly said, okay. And that was a good decision for progress of science, but that was not necessarily a good decision for business in the sense that IBM did not make a lot of money out of these machines, let's say, because people could not program it. But I mean, it was actually, they were the leading company at that time in doing out-of-order execution. So the major difference today is precise exceptions. Basically, what we did yesterday is really critical for the success of this sort of machine, because you need to reorder the instructions at the end. And this is provided by later works that actually show that you can do out-of-order execution with precise exceptions together. I'm going to essentially describe things without precise exceptions first, because it's easier to discuss. But then we're going to talk about precise exceptions a little bit more. But yesterday's lecture is directly applicable to today's lecture, actually. So as a result, out-of-order execution variants are used in most high-performance processors today, starting with the Intel Pentium Pro, and then AMD followed up with K5. But almost all high-performance processors today use it. So this is how things will look like. Basically, we're going to decode instructions. We're going to put into the reservation stations. This is called a scheduling buffer, if you will, abstractly. So this part of the pipeline is still in order. And then we're going to dispatch instructions when they're ready in out of order. So this part of the pipeline is completely data flow driven. And we're going to reorder instructions at the end, write the results into the reorder buffer. But you can see that when an instruction finishes, it's going to broadcast the tag and the value so that dependent instructions can get the tag and the value they're waiting for. That's how we will actually communicate the readiness of a value. When an instruction finishes, it's going to broadcast, oh, I'm producing this physical register X. And if you're waiting for physical register X, better capture the value that I'm sending. Okay? So that's how we will communicate. This is the data flow communication internally. So there are two humps over here. One is the reservation stations, which is the scheduling window, and the other is the reorder buffer. This is also called an instruction window or active window. Basically, reservation stations hold instructions that have not been scheduled yet. Reorder buffer holds all instructions that have not been retired yet, that have not updated the architectural state yet. I like thinking of this as a camel like this. If you want to remember a pipeline, out-of-order execution pipeline today, this is the scheduling buffer over here, and that's the reorder buffer. Of course, it doesn't work this way in a camel, I believe, but it's kind of a pipeline also. Anyway. Okay, so that's the general organization. This is from your paper that I've assigned. A lot of things will become more clear today, but today's basically the purpose of me showing this is existing processors do this. Basically, this is the renaming and dispatching, for example, and these are the reservation stations over here. They called instruction buffers, and these are the functional units. And then they have separate register files. We're going to get back. And then there's a reorder and commit over here, as you can see. Today, we're not going to talk about the memory interface. It's going to complicate things, and that's the optional lecture. And Thomas Sowell's machine was kind of similar, except it's looking at just the floating point units over here. We're going to look at something like Thomas Sowell's machine, actually. We're going to look at multiply and add over here. Okay. And you can see that this actually had impact in the real world, even though it was commercially generally not very successful. IBM 3691 was used in supercomputers at the time in 1960s for space exploration, for example. And you can see that at the time computers used to be huge. Right now, this thing is more powerful than that entire room. It's amazing, right? Okay, so recall once more. We're going to rename registers, basically. I've already gone through this slide multiple times. I'm not going to go through this. But basically, register ID is going to be renamed to reorder buffer ID or reservation station entry ID. For the rest of this lecture, I'm going to use reservation station entry ID, not the reorder buffer entry ID. After renaming, we're going to use the reservation station ID to refer to the register. So basically, for this, we need a register rename table called a register alias table. And you've seen this already. I've kind of reordered the fields over here. But basically, you have register 0 to register 7. This says whether it's valid. If the valid bit is set, the value in the table is correct. It can be trusted, basically. Otherwise, tag specifies where to find the correct value. That's the name. That's the new name. Tag is a unique name for the value to be produced. That's how you do renaming. And recall from precise exceptions lecture, we essentially have the same thing. Register file or register alias table. You can think of it that way. We're going to separate things more later on. But let's start with this. So this lecture. So let's now go through an example. In this lecture, we're going to look at the register file or register alias table, RAT. Tag is the pointer to the reservation station entry that will produce the value. So I'm going to introduce reservation stations over here soon. And for simplicity, we will ignore the reorder buffer. We'll add it later, but adding it is relatively easy, actually. We're just going to ignore it for now. So Thomas Sowell's algorithm, this is actually a full definition. Maybe I'll go through this relatively quickly. But basically, first you need to check whether a reservation station is available before renaming. And rename an instruction only if a reservation station is available. Only if a buffer is available so that you can put the instruction, basically. Otherwise, you stall. While in reservation station, each instruction watches a data bus called common data bus for the tag of its sources. When tag is seen, it grabs the value for the source and keeps it in the reservation station. When both operands are available, instruction is ready to be dispatched. I think I've kind of said this before. You dispatch the instruction to the function unit when its instruction is ready. And after the instruction finishes in the function unit, there needs to be some arbitration for this common data bus. We will see that, or you need to have multiple common data buses, as I will show you. The instruction puts the tagged value onto the common data bus. This is called a tag broadcast. Register file is connected to the common data bus as well as reservation stations. And register contains a tag indicating the latest writer to the register, as we have seen. If the tag in the register file matches the broadcast tag, we write the broadcast value into the register and set the value. And then eventually a rename tag needs to be removed so that some other instruction can get allocated to the reservation station. Okay, so this is one quick overview of the algorithm that we're going to look at. So we're going to do the exercise. Basically, we're going to execute this sort of algorithm on this code. As you can see, this code has a multiply, and then it says an add over here. This add is dependent on the multiply because it's sourcing R3. And then it says a bunch of instructions that's independent of the add, but there are dependencies internally between the instructions. For example, this last add is dependent on this multiply. We're going to assume the add takes 4 cycles execution. Multiply takes, I think, 6 cycles execution, sorry. If we're going to assume 1 adder and 1 multiplier. So if you actually need to do the calculation in a non-pipeline machine, this takes 50 cycles. Non-pipeline machine says you have 4 add instructions and 2 multiply instructions. Each of them takes, let's say, 7 cycles versus 11 cycles, and it's 50 cycles. That's an approximation, basically, because you can actually make the non-pipeline machine nicer without the clock cycle, without the clock boundaries. But with this assumption, it takes 50 cycles. We're going to look at an in-order dispatch pipeline machine with imprecise exceptions, no forwarding and forwarding. And then we're going to simulate an out-of-order dispatch pipeline machine with imprecise exceptions. No reorder buffer, as we said. We're going to use forwarding. Okay, so let's take a look. This is an in-order dispatch pipeline machine without forwarding. So you can see that this is the first multiply. The second add is dependent. So without forwarding, it needs to wait for the previous value to be written into the register file, and then it gets decoded, as you can see. So if you actually go through this yourself, which you could, it takes about 31 cycles. So basically, in-order dispatch pipeline machine without forwarding is much nicer, let's say, than the 9 pipeline machine, right? 50 cycles worth 31 cycles. This is cycle count. Clock cycle is a totally different issue. I'm assuming that they're all equal for now. Now, if you actually add forwarding to it, this instruction can start executing after the value is forwarded from the prior pipeline stage, depending on some forwarding rules, if you will, and you can actually reduce it to 25 cycles. I'm not going to go through these, but you can actually do these with calculations yourself. And we actually have a lot of exercises similar to this. So can we do better, basically? Can we actually reduce this 25 cycles? This is what we have built so far. Can we reduce this 25 cycles further? And the answer is yes, basically. If you use out-of-order dispatch, out-of-order execution, it's going to look like this. So basically, this instruction is going to wait over here, but this next instruction can be dispatched and executed while this prior instruction is waiting. So if you out-of-order dispatch pipeline machine with forwarding, we will get down to 20 cycles. This picture is actually a little bit slightly misleading because you don't really need the write back stage, actually. So it's actually 19 cycles. If you have this imprecise, if you're going to use what I'm going to describe, you don't really need that. So it's about 19 to 20 cycles, which is not bad. So the key difference is going to be here, independent instructions wait, as you can see, but here the independent instructions can execute. Okay, so let's see how this works. Now, in prior times, I would use the blackboard, but now we have a nice animation over here. So we're not going to use the blackboard, we're going to use the animation. So this is going to be our first out-of-order machine simulation. Now let's first set up the stage. So this is our register file initially. We're going to call it the register alias table. You can see that all values are valid. And the values are the same as the register numbers, if you will, for now, just for fun. This is a program we will simulate, which is exactly the same as what I showed you over here. It's written in a slightly different font. And these are the reservation stations. So these are things that I have not introduced so far, but let me introduce them. So this is, we're going to assume 1 adder and 1 multiplier. We're going to assume they're pipelined. So you can start 1 instruction every cycle in the adder and multiplier. And the principle of pipelining applies to functional units also. If you start 1 instruction in 1 cycle, if the adder is, for example, pipelined over 4 clock cycles, you can start the next instruction in the next clock cycle, and they could be executing in a pipelined adder. We didn't talk about how to pipeline an adder, but the principles are very, very similar to pipelining an instruction processing engine. So, okay, so this is the reservation station for the add unit. We're going to assume 2 sources for add, clearly. These are different reservation station entry numbers, A, B, C, D. And each reservation station entry has, for each source, a valid bit, is the source ready? A tag, if the source is not ready, who will be producing it? Which tag will be broadcast, and which tag should I be looking for? And the value if the source is actually ready, right? And you have two sources, so you have valid, tag, and value fields for each source. So if you look at this, it's very similar to the register file, right? So basically, register file stores some values. Here, we actually copy those values over here and wait for values that are not available yet. And we're going to do exactly that. And that's true for the multiply unit also. You have valid, tag, and value for source 1, valid, tag, and value for source 2. And when an instruction starts executing in the adder unit, we take the value, two values that better be ready for execution. And then we actually take the destination tag that we're going to produce. So for example, if this instruction over here starts executing, we're going to broadcast tag A, saying that, oh, this is the value the instruction at reservation station entry A is going to produce. And anybody who's waiting for A is going to capture that value. Does that make sense? So we're going to rename these registers to reservation station entries that are holding the instructions that are going to produce the values of those registers. That's the idea. Very similar to the reorder buffer, except this is the reservation station. That's true for over here also. You can see basically add and multiply execution units have separate tag and value buses. So we're going to be able to broadcast one tag and one value per cycle from this unit, and one tag and one value from this unit as well. And you will see that it's going to be a mess, because these tags, when they're broadcast, need to, let's say, follow my, cursor, need to be going to these tags. You need to be comparing this. And then you need to be comparing these tags to the broadcast tag, and then these tags to the broadcast tag, and then these tags to the broadcast tag, and these tags to the broadcast tag. So if there's any instruction waiting for the tag you're broadcasting, and if the value, if it's not valid, then it better capture the value that's also being broadcast. So values are also going to be broadcast this way. So there'll be long buses that are going to go over the entire machine, and you will see this soon. And that's the cost. It's expensive, actually. And if you're doing 2 broadcasts per cycle, you don't have only one set of buses like this, you have 2 sets of buses. In existing machines, there are more than 8, 10 functional units. So we do these broadcasts every cycle, 8 or 10 instructions, let's say, potentially. So existing machines are much more complicated than what we're going to simulate. But these exist, basically. You can see how existing machines are so powerful. Okay, is this all good now? I have not started the simulation yet. I've just set up the stage. Okay, initially reservation stations are all invalid. So I don't show the invalid bits for the reservation stations, but there needs to be a separate allocation mechanism for reservation stations, which reservation station entry is free or not. I'm not showing that over here. Because we're not going to actually deal with that in this particular case. We have a small program that fits in the reservation stations right now. Okay, so this is the setup of the stage. Any questions? Now we're going to simulate. This is cycle 0. Clearly, no instruction has been decoded. Let's fetch the first instruction. In cycle 1, we fetch this multiply instruction. Nothing interesting really happens because we just fetch the instruction, right? The interesting thing happens when we decode that instruction, right? Now we're going to decode this multiply. Now, what does decode mean? We've already gone through the algorithm. Let's go through the steps. Multiply gets decoded and allocated in the reservation station X. Why X? Because this is the multiply reservation station, and this is a multiply. So that's the function of a decoder. And X happens to be free, so let's allocate it over there. Now, what does that mean? So, okay. We basically need to check if the reservation station is available. In this case, we assumed it's available. Yes, that's good. So we allocate multiply there. The second step is we access the register alias table to get the sources. We access it with the first source, R1. R1 is valid. That's good. So we can trust the value. Tag doesn't matter because it's valid, right? Looks nice, right? We basically copy the valid bit saying that the source is ready and the value is 1. Tag is, we don't care again. It could be any garbage value. It doesn't matter. We're not going to check it, basically. We do the same thing for the second source. Okay, before I said that, step 3 is put the source registers into the reservation station X, right? I just showed this to you for the first source, but we do exactly the same thing for the second source. It's valid, the value is 2. So we basically copy the register file entry or register alias table entry to the source 2 over here. Sounds good. Now, we also need to rename the destination register, which is R3, to X, just like we did yesterday. Basically, R3 is not valid anymore because multiply is going to produce the value of R3. And anyone who wants the source, who wants to get the value of R3, better capture the tag X when it's broadcast. That's what this means, basically. So anyone who's going to read R3 now is going to get X as a tag. So basically, this is R3 is now renamed to X. Its new value will be produced by the reservation station that's identified by tag X. And anybody who's going to consume that value is going to refer to that as X. And we'll see that very soon. Okay, this sounds good. Now, the other realization here is that multiply in the reservation station X is ready to execute in the next cycle because both of its sources are ready, right? So there needs to be some other logic that detects this. This is called the scheduling or readiness detection or instruction wake-up logic. Again, I'm not showing you, but there needs to be some other logic to detect whether which instructions both sources are ready and which one should be selected out of them, okay? Okay, so that was cycle 2, which was a little bit more painful than cycle 1, as you can see. Cycle 8 will be the most painful for us, as we will see soon. So cycle 3, we figured out that multiply can execute, that logic that I mentioned, figured out that this multiply can execute. Let's start executing it. Multiply in reservation station X starts executing. Basically, you need to check the readiness, both sources are ready. You need to wake up the instruction. There needs to be some logic that does that. And then you supply the values and the tag it's going to produce, which is going to be X, right? So this multiply is going to take 6 cycles. Because it's ready, it will be dispatched to the multiply unit. But after 6 cycles, it's going to produce the value as well as the broadcast tag everywhere, as we will see. And that's going to be cycle 8, I think. Okay, so concurrently, in the decode stage, we're going to decode the second add instruction. Let's take a look at how that happens. Add gets decoded and allocated into reservation station A because it happens to be free, as you can see. Decoding is very similar. So add sources R3 as its first source. You take valid bit as 0. It's not ready yet. Tag is X. Value, I don't care. Basically, this means that I'm waiting for the instruction that's producing it, which is in reservation station X, right? This source is not ready, but reservation station X is going to produce it. And when it produces it, it's going to broadcast the tag and the value, and I better capture that, okay? The second source is, let's say, that went very fast. The second source is R4. It's very similar to earlier cases. Basically, it's valid, the value is 4. But this add cannot execute because one of its sources is not ready. So it's going to wait. Basically, we do the same steps, 1 through 4 in the prior slide for add, and we rename also R5 to 8. So now R5 is going to be produced by the instruction that's in reservation station 8, which happens to be this add. Okay, now anyone who's going to source R5 later on, which you will see this, one of these instructions, I think this one, it's going to refer to value A or tag A. Okay, so add in reservation station A cannot execute in the next cycle because one source is not valid. Sounds good, it's fine. Now let's take a look at the interesting case over here. In cycle 4, this multiply here is happily executing. Add in reservation station A has to wait because one source is not valid. Now we can decode the next add. Let's take a look at what happens. Decode, again, we take the first source register, register 2. It's valid, and the value is 2. We take the second source register, which is register 6. It's valid, and the value is 6. Now this can execute, right? It doesn't matter whether the previous instruction couldn't execute, it got out of the way. That's the good part. Now we also need to rename, while we're decoding this add instruction, rename the destination register R7, and we rename it to B, because we allocated it as a reservation station B for it, okay? So this register 7 is invalid, and it's renamed to B. Now add in this reservation station B is ready to execute in the next cycle. And then wake up logic determines this, and we will see that it's going to start execute. It will start executing out of order, or it'll be dispatched out of order to this functional unit earlier than a prior instruction. Okay? I'm ignoring the fetches because in the fetch state you don't do anything useful. That's useful for the purpose of this picture. Okay, now let's go to cycle 5. In cycle 5, multiply is still happily executing over here. This first add is still waiting. Now the good thing is the second add, we're able to execute it. And that's the big benefit of out-of-order execution right now. This was not possible in our earlier pipeline designs. Here, the wake-up logic determines that this add in the reservation station is ready because both of its sources are ready. One source is 2, the other source is 6. After 4 cycles, it's going to broadcast its tag B, and the value that's going to compute after 4 cycles. Okay, and whoever is waiting for B, this one, for example, is going to capture that value. Okay, we're going to see that. And then we decode the next instruction. I'm going to go through this relatively quickly because the process is very similar. You can see that the next instruction sources R8 and R9. Okay, and yeah, we went through it very quickly, as you can see. We basically take the register file, register alias table entry R8 and R9. They both happen to be valid, and the values are 8 and 9. So this instruction in reservation station C is ready to execute in the next cycle also. That's also independent, basically, of prior instructions. So that's good. In cycle 6, this multiply is happily executing still, because multiplication takes long. This add is waiting. The second add is executing because it started execution out of order. And now this third add can also start executing. That's the good part again, right? This is enabled by out of order execution again. This third add starts executing. And again, we don't show that over here because you can guess. So the reason it can start executing is multiple. One is out of order execution machinery that we added, and the second is adder is pipelined. Because the previous add is in the it moves to the second stage of the pipelined adder, and the second add moves to the first stage in the pipeline adder. Okay, so there's pipelining happening in the adder also. Alternative is providing a second adder, of course, right? Like we have done in the earlier parts of pipelining, if you remember with the dryer, right? Okay, so we decode this multiply. This multiply is interesting because neither of its sources are ready. So if you index the register file R7, it's not valid, but it's going to be produced by B, tag B. And R10 is not valid, but it's going to produce by C. So neither of its sources are valid, so you cannot actually start executing it. And we rename R11 to Y, because that's the reservation station entry that's going to produce that value. So 0Y. So you can see that the register file has a lot of invalid values right now, because we actually put a lot of instructions that are going to write to different registers into the reservation station, and they have not produced those values yet. Okay, cycle 6 is done now. Cycle 7, let's take a look at it quickly. Multiply is executing, add is waiting, the next add is executing, the next add is also executing. The next multiply cannot start execution because it's not ready yet, as you can see, 0, 0. And then the next add is decoded. If you look at this next add, its sources R5. R5 is invalid and the tag is D. Wait a second. No, sorry. Okay, something interesting happened here. I should have animated it nicely. When its sources R5, R5 is invalid and it's going to be produced by A, right? So we actually put it over here. And then R11 is invalid and it's going to be produced by Y. So this is going to be 0Y. And we need to rename R5 also. So it's reading R5, old value of R5, and it's going to produce a new value of R5. So it's going to read the value from produced by A for R5. It's going to produce a new value for R5 coming from reservation station entry D. Okay, so interesting thing happened to R5 basically. Okay, so nobody will get the wrong value over here because we're always updating or renaming the registers in program order. So also at this point, all 6 instructions are decoded and renamed, as you can see. Note what happened to R5. It was renamed twice. First, it was renamed to A, which is here, which happens to be this instruction that's producing one value, one definition of R5. And then it was renamed at the end by this instruction to D. Okay? So all of the instructions that are in between these two renaming of R5 are going to get the first definition of R5 because they're referring to A, right? Because they were renamed using this definition of R5. All of the instructions that are going to source R5 after this add are going to get the value from D, okay? Okay, but we don't have such instructions because we're done with the instructions right now. Let's take a look at cycle 8. So cycle 8 is the fun part because some instructions are completing right now. So in cycle 8, multiply in RSX is done, or we're going to assume it's going to broadcast this tag in this particular cycle. That's the assumption over here. It could be a different assumption in some other machine. But basically, this multiply is done. Its value, the result is 2 because it's multiplying 1 times 2. And it's going to broadcast that value as well as the tag. Now let's see what happens with the broadcast of the tag, X. So X is going to be broadcast to all of the fields that have tag in them. Now we're animating, you can see some of them are actually capturing X, right? So whoever is waiting for X is highlighted over here with yellow. This register 3 is waiting for X because it's going to be valid after that. It's invalid, and the tag is X. This instruction is waiting for X because it was renamed that way, and it's going to capture the value. Now, the value also broadcasts concurrently. This happens concurrently, actually, but I'm showing it serially because we have bandwidth problems, let's say, or animation problems. So we broadcast multiplies results, and anybody who was waiting for X captures the value too. Okay? So basically, that's how we communicated the value. By broadcasting the tag and value concurrently, any location in the machine that had a valid, that was invalid and waiting for that tag captures the value. Okay? So register 3 became 2 and valid. And this source 1 in reservation station entry A became 2, value became 2 and valid. And now this entry, this add in reservation station A is ready to execute in the next cycle, right? There's some logic that determines that. That's the wake up logic. So that's beautiful. This is how we communicate the value. This is also how we communicate the dependence. So we're communicating two things at the same time. Dependent instruction you can execute, and the value, here's your value. Okay? But that's not all. Unfortunately, it also happens that add in reservation station B is also done here because of the length of the instructions. Basically, it also needs to broadcast. And it needs to use separate tag and value buses to do the broadcast. So this is the add that we're talking about. It's adding 2 and 6, as you can see. After 4 cycles is done, the value is 8, and it's going to broadcast this tag B. Same thing. B gets broadcast to all of the locations that have the name tag there. And if it's invalid, it becomes valid soon after the value gets in. So it turns out that instruction is also waiting for B over here. But basically, you have to broadcast it everywhere that may be potentially waiting for the tag. Now you can see the logic complexity and the wiring complexity, right? These wires need to run around everywhere. And the logic, that comparison that I kind of show is really a comparator. And we've seen that comparator, right? Equality checker, essentially, in lecture combinational logic. Okay, so we also broadcasted value, of course, and everybody who was waiting for tag B captures the value 8. Now that looks good. Our register 7 becomes 8. This instruction, one of its sources becomes valid, but unfortunately the second source is still invalid, so it cannot execute. So it needs to wait for the second source. Okay. Okay, so nothing else that's interesting happens in cycle 8, let's say. The other instruction is executing, multiply, the other instructions are still waiting. Okay, cycle 9. This write back doesn't necessarily need it, basically, because we actually already wrote back the results of multiply, which was actually updating. What did we update? Sorry. We updated register 3, right? Yes, register 3. So this write back is not strictly necessary. But in a reorder buffer based machine, you need to actually put it in the reorder buffer somehow. But that could also happen in the prior cycle. But I'll keep it for completeness for now. So if you may have questions about this write back, keep it for completeness over there. So this new instruction starts, the second instruction starts executing right now because both of its sources became valid, right? So it gets sent into the functional unit. And this next instruction also does write back. This instruction finishes and it broadcasts and updates. It broadcasts. Yeah, I think I don't animate these further because it actually takes a long time to animate everything. But this instruction, if you remember, it was actually this instruction, reservation station C. It broadcasts tag C. So everywhere with tag C captures value 8 plus 9, which is 17. So this will become 17, and this will also become 17 in this cycle, and it does. That's good. And then this is still waiting. So multiply in RSY is now ready to execute in the next cycle, right? Because both of its sources are ready over here, and the wake-up logic determines that. Okay, now you can keep the animation going further and further. You can see that the instructions are still executing. And when an instruction finishes, it broadcasts its tag and value and updates things. So this was this add over here, right? Well, I guess this was the add that's doing R3 plus R4, R5, which is this one. It broadcasts the tag A, and everybody who's waiting for A gets the value, and it's still not ready to execute, as you can see, that instruction over here. Okay, so I'll go through this relatively quickly at this point. But basically, when an instruction finishes, it broadcasts this tag and value, and anybody who's waiting for the tag and value gets that updated and checks for readiness in the next cycle. And for example, here in the cycle 15, this multiply finally becomes, finally broadcasts this tag, Y, and the value 136, and everybody who's waiting for Y and 136 captures it. And now this instruction becomes ready to execute over here, which happens to be this instruction. And if you actually follow its execution, eventually it broadcasts its tag in cycle 19, and tag is D, and the value is 142. And now at the end of the execution of all of these instructions, all of these are valid, as you can see, because we're done with the program, this toy program, and all of these should be deallocated, but we didn't show the deallocation of the reservation stations. Does this make sense? So that's the beautiful part. And if you don't ignore the writes over here, it's 20 cycles as promised. Okay, so now you know how auto execution works, right? It's not that complicated once you understand the concepts of renaming and value and dependence communication. Let me handle some questions here, and then we're going to take a break. Actually, we should probably take a break. But let me cover these questions very quickly. So what is needed in hardware to perform tag broadcast and value capture? Basically, you need to make a value valid and wake up an instruction. For this, you need wires, comparators, and logic. Basically, a lot of hardware. And this is expensive hardware. Does the tag have to be the ID of the reservation station entry? Basically, I said that this is not necessary. As long as you can link the producer to the consumer with a correct and common tag, that's fine. It could be the reorder entry actually over here. You just need to connect the producers to the consumers accurately. In this case, we happen to use the reservation station entry, but it could be any unique name that enables linking of the producer to the consumer. It doesn't need to be even anything specific to the hardware, specific to any buffer. It could be some namespace, basically, that you happen to allocate and deallocate. What can potentially become the critical path? Well, this is actually what people have optimized over years and years. Tag broadcast. You broadcast the tag, somebody needs to capture the value, and they need to wake up. That loop is actually very long because the wires go through essentially the entire machine internally, and there are comparators all over the place. And then you need to actually also determine the wake up. So this is also called a wake up, tag broadcast, wake up, and select logic. And this is one of the most critical parts of the machine internally. How can you reduce the potential critical paths? More pipelining and prediction. And existing machines do all of this, basically. The existing machines are very sophisticated. They sometimes even predict which instruction is going to broadcast this tag. And the reason they do it is because for example, loads. We didn't discuss loads over here, but how do you decide when a load is going to broadcast this tag? Is it going to hit the cache? Is it going to hit in the first level cache? Is it going to miss in the first level cache? So it actually complicates the scheduling logic significantly. Okay, so basically, this is our example. You can draw the data flow graph of this above code clearly, right? But when we come back from the break, I'm going to give you just this picture. We actually constructed this picture. This is in cycle 7. At the end of cycle 7, we have exactly this picture earlier when we actually done the simulation. By just looking at this, you can construct the data flow graph. And you can start thinking about how doing your 10 minutes of break. You can also provide the executing code in sequential order. So we're going to start doing that after the break. And in the end, we'll have something like this basically. Okay, so let's take a break until 15:20. Well, no, 15:30. 15:20 would be less than 1 minute. 15:30, and then we'll be back construct related to reservation station deallocation. So let me cover that first. So in this example that we went through, the machine simulation, I did not show you how the reservation stations are deallocated, but they have to be deallocated at some point. And it makes sense to deallocate them when an instruction has broadcast its tag and value. It doesn't make sense to use them afterwards. So you can deallocate them at that point. Unless that was done speculatively. In modern machines, actually it's done speculatively. So they really need to keep the reservation stations for longer than that. But we didn't deal with that. But you need to deallocate the reservation stations so that incoming instructions can be allocated into the reservation stations. Because if an incoming instruction that's being decoded cannot be allocated a reservation station entry, you need to stall the pipeline, right? So the size of the reservation stations and how you manage them is important for performance in the end. You can think of the size of the reservation station as how many instructions can you buffer before you stall, right? If the size of the reservation station is actually 2,000, for example, you can buffer 2,000 instructions before you can stall. So the longer this is, the larger the reservation stations are, the larger your latency tolerance is. So it's actually important, and people are trying to increase the size of the reservation stations today. In modern machines, they're actually much larger. But the reservation stations that are most critical are load and store reservation stations, which we don't deal with here. But you can watch the optional premiere lecture about that, which will give you an idea of how complex the load and store reservation stations are. You need to deal with addresses, for example, in load and store, which we don't deal with over here. We deal with registers. Dealing with registers is a lot easier than dealing with large memory addresses for multiple reasons. If you watch the lecture, you will see, because registers are statically determined, but the address of an instruction, address of a load instruction is determined dynamically. Remember the base plus register calculation? You determine the address dynamically, so you don't know which instructions are dependent on that instruction, right? Here, we know exactly with the registers. It's beautiful. But with memory, it becomes very, very messy. Okay, I'll leave it at that for now. So we handled these questions. So as I promised, so if I give you this code, you should be able to draw the data flow graph. That's a forward problem. I'm not going to do that, but I'm going to do it in a reverse way. Basically, this was the state of the register alias table and reservation station in cycle 7 in our simulated program. And if somebody gave this to you and asked, what code is in the machine right now? You could actually draw the data flow graph. And that's what we're going to try to do right now, very quickly. I have the answer in the next slide, but I'll do it over here quickly so that you can see. And these are actually good problems also for exam, if you will. I know you're not studying for the exam, just for the exam, but these reverse engineering problems are actually a good way of testing understanding of the concepts, because you really need to understand how the machine works, I think, to figure this out. Okay, so let's try to switch. So this is basically cycle 7. Just to remind you, this is our cycle 7. And now we're going to draw the data flow graph of this thing. Let me see. I have lots of colors. I love colors. I'll start with pink or purple. Pink. Okay, so how do we do this? It's actually pretty easy, but okay, you see that? Okay, I can fit two things. We're gonna do this. So what is a data flow graph? Data flow graph is a bunch of nodes, right? So first of all, by looking at this picture, you know that there are 1, 2, 3, 4, 5, 6 instructions in the machine, right? We're assuming that somebody needs to tell you that they're just decoded, but not, they're just recoded and renamed, but nobody started execution or something like that, basically. So all of the instructions are renamed. So we have 6 data flow nodes somehow. Let me draw those. I don't know, maybe color code them. Okay, I don't want to do the color coding right now because they're going to be connected in different ways. And you can start anywhere, actually, because in the end, this is data flow. Actually, let me start with, I don't know, let's start with this add, this poor add. So this is the pink instruction that refers to this. So what do I know about this instruction? Source 1 is tag X. I don't know the register number yet, but I have a pretty good idea that this could be the register number, and it probably is. And source 2 is valid, and its value is 4. I don't know where it's coming from, but I may have a good idea that it may be coming from here, right? Register 4. So does that make sense? Maybe I should just say that there's a good idea. Maybe this is register 4, and maybe this is register 3. I'm probably right. So somebody's going to produce X, right? So this add cannot be the first instruction that's executed, assuming the machine is correct. So let me go to X then. Maybe I started in the wrong place. I don't like this color because it's too similar. Okay, let me go to X. So I should also say that this is an add, right? What do I know about this? It's an add, and it's going to produce A. And what's A? It's going to produce something it's going to produce a tag that's not in the register file. So somebody overwrote the register that this is writing, right? So I know a lot of information, as you can see, just by looking at this reservation station entry. And now that tells me also to look at this reservation station entry because it's going to be the input of this instruction that's in this reservation station is going to be produced by this reservation station. And let's take a look at that. It's going to produce X. And I know that this X is going to get connected over here. That's good. And one of the inputs is 1. And the other input is 2. And they're both ready. That's good. And I kind of have a suspicion by looking at the register file that they may be actually R1 and R2, right? Maybe this is R1, maybe this is R2, right? Because there's no other 1 or 2 value over here, right? It's constructed that way. Okay. So now I know these data flow nodes. This is a multiply. Okay. Now, who am I going to go to next? Lou. What should we do? Should we do this one? This looks interesting, I think. Let's do another add. Because both of the sources are ready, actually. So let's put this add somewhere over here. Again, I don't know much. I'm not thinking that much. One source is 2, it's ready. The other source is 6, it's ready. How do I know that? These valid bits, right? And again, I have a suspicion that, oh, this could be R2, this could be R6. What do you think? And it's going to produce B. And B, probably it's renamed R7 into B, right? I'm going to do that. Let's keep the question marks. You can validate the question marks later, right? Okay, so this looks like this is independent of all of these over here. Okay, let's go to another instruction, another color. Thanks for getting this because this is a lot of nice colors. Okay, another color. What should I start with? I want to do this one because I know that both inputs are valid, right? So this is another one. This is another add, as you can see. And then this add, can you see that? Okay, barely. This add has 8 over here as one input, it's ready. 9 over here as another input, it's ready. And again, I have a suspicion that this could be R8 and R9. R9, okay, and it's going to produce the tag C. And this C is probably R10. Okay, that sounds good also. Okay, now let's go to something else. Let's go to this multiply. Can you still see everything? I don't like this color again. Even with all of these colors, as you can see, we're running into color collision, or maybe it's because the granularity of my eye in determining colors is not very good. Okay, we can push this up. Okay, now we're going to try to figure out what that instruction is. It's a multiply for sure. One of them is B, the other is C. Oh, look at that. This B can come over here. And this C can come over here. It's kind of a messy data flow graph, but it's a data flow graph, right? And both of them are not ready. And what are they? R7 and R10 probably, right? And we already kind of guessed that. R7, R10. Now it's getting more solidified, if you will. Now let's take a look at the last one. Last one, orange. Last instruction is this, D. And what is that? Is an add. Where should I situate it? A and Y. Who's producing Y? Oh, I forgot something in the previous one. Sorry, that's why. So this is also producing Y, which is, if you look at the tags over here, R11, right? Okay. Now, the last one, I kind of have a guess. It's going to get A and Y. A is being produced by this one. Y is being produced by this one. It's a add instruction. So it's going to get connected like this. That's the beauty of colors. You don't overlap the lines, right? So this is A, Y, and the output is D, which is R5. Okay? So now we actually have the data flow graph. This is the full data flow graph of the program that is in the machine. It makes sense, right? And I just drew this data flow graph by looking at stuff. I didn't even think about it, right? I started with the second instruction, actually. I didn't start with the first instruction that's in the program. Now you can start reordering these instructions and find the instruction sequence. And you can verify the verify which registers, but eventually you'll come up with this thing. But basically, the first instruction is this multiply. This multiply R1, R2, and the result goes to X. X is R3. We forgot that kind of, but you can also verify it from here, R3. And the next instruction may be this one, although we're not sure because this instruction is completely independent, right? So this instruction can be anywhere. So we don't know the complete instruction ordering over here, but we can guess some orderings. So clearly this is before this one, and 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 this is before this one. right? So based on the dependencies, you know the ordering, but you don't know the complete ordering of the instructions. Again, I don't want to go through this and come up with all of the instructions since I want to cover other stuff. But you can basically write all of the instructions that we have over here. Let's do that. This multiply we accounted for. And then this, what is this? This is an add, R2, R6. Oh no, this R2 is not correct. So you got to be careful with that one, right? Yeah, actually it's correct, I think. Yeah, add R2, R6, R7. Yeah, sorry, it's correct, but maybe the ordering is not correct, as we discussed. And this add is, let's see, I should have color coded these, but sorry. And this add is over here, add R3, R4, oh, and the result is A. What is A? So that's the part we don't know. How do you figure that out? I'll let you figure that out. So somebody got renamed and tag A is kind of lost. I need to figure that out somehow. What is this? What register does this correspond to? I'll let you think about that. But basically there's something over here, okay? And then you need to actually go through these instructions. This is add R8, R7, R8, R9, and the result is R10 over here. We accounted for this one. Did we account for this one? Yeah, we account for this one, except the destination. And then this one is, this is a multiply, another multiply. I don't know if you're seeing this. I think you're seeing it, but this is a multiply. What are you multiplying? R7, yes. And then R10 over here, yes. And then the result is R11. So it's going to be very similar to what we find out. And then the final one's over here. This is, wait a second. This is an add. One of the inputs is A. I'll keep it as A. And then the other input is Y, which is R11. And then the result is R5. Okay? So then the question is, what could A be? Can you figure out it's R5? Anybody? Remember that R5 got renamed twice because we actually simulated this before. And actually, you should be able to figure out that it's R5. Why? Because all of the other instructions have produced their values and they're being used. But this is overwriting some value. It must be reading actually the same value that's overwriting. So you need to do this by process of elimination. Does that make sense? Okay. Okay, I'll let you figure that out. But this is your data flow graph, and unfortunately not the perfect ordering because our real ordering was this one, right? So I couldn't really decide the ordering of this instruction because this is the data flow graph, right? Yeah, now this also proves that this machine is a data flow machine internally. Internally, what we have is a data flow machine executing a data flow graph, okay? Hopefully this was clear. You can actually do this on your own, and I would recommend doing that on your own. But now we'll have to move. Any questions? Okay, so now we've constructed the data flow graph. This is a much nicer version of that data flow graph, let's say, maybe not as colorful. But what we've done is we reverse engineer the data flow graph of the executing code, sometimes not perfectly, because we cannot reorder the instructions exactly. As I showed you, I got the reordering wrong between these two instructions because they're not there's no dependence relationship between them. I cannot figure out that relationship unless somebody tells me some other information, right? Okay, so basically there are a bunch of other questions over here. We discussed one of these. When is the reservation station entity allocated? Should the reservation stations be dedicated to each functional unit or global across functional units? That's another question, basically. And this is actually interesting because this goes into, should a buffer be centralized or should it be distributed? And there are trade-offs related to this. If it's centralized, it's a huge buffer. Everybody goes through it. The dynamic utilization of the buffer may be good. But if it's distributed, it's just now each of them are smaller buffers. So actually the latencies may be easier to handle. Energy may be lower. But now, and also you can specialize the buffer to the functional units. For example, load instruction require addresses. Add instructions don't require addresses, right? So you don't need to store the address inside the buffer, right, for add reservation stage. So you can specialize. But unfortunately, when you have distributed buffers, the load balance becomes a problem. So if everything you're executing in the machine is add instructions, and you may not have enough add reservation stations, right? Because you've distributed the buffers across the functional units. So there are trade-offs over here. Another question is, should reservation stations and reorder buffers store data values, or should there be a centralized physical register file where all data values are stored? This is a loaded question because we're going to build up to this, actually. So values are going to become problematic, as we will see. Timing is also problematic. I'm not going to deal with timing. Exactly when does an instruction broadcast is tagged? When do you know this information? When should you broadcast the tag and when should you broadcast the value? Should these be done concurrently or in a serial manner? So there are many, many design choices that we're not going to tackle over here, but existing machines actually tackle in very, very interesting and nice ways. There are a lot of tricks you play to make this more efficient, more lower latency, and less costly. But again, we don't have time, and this is the first course you're taking on the topic. Okay, basically, we did this exercise. That's great. Hopefully, you can do it on your own, and I would recommend that. An exercise for you is to do the same exercise with precise exceptions. It's not going to be that different, frankly. You need to add a reorder buffer stage into the pipeline, but it's not going to be that different. It's not going to change the timing that much also. But let me talk about out-of-order execution with precise exceptions. What does it require? So the idea is very similar. Use a reorder buffer to reorder instructions before committing them to the architectural state, just like we did yesterday. Yesterday, we added this machinery to a multi-cycle execute pipeline machine in order dispatch. Here we have out-of-order dispatch with the reservation stations, right? So an instruction updates the register alias table when it completes execution. This is also called a front-end register file. So I'm going to describe something to you that is slightly different, that is employed in all processors today, almost all processors. So basically, an instruction updates the register alias table when it completes execution. This basically says that where can the prior instructions get the value from? This is called a front-end register file, and we will see this with an example. An instruction updates a separate architectural register file when it retires, when it actually is the oldest instruction and finishes without exceptions, as I said earlier. In other words, the architectural register file is always updated in program order. So there are two register files, front-end register file, architectural register file. And front-end register file is updated when you actually broadcast your tag. And the architectural register file is updated in program order from the reorder buffer, okay? On an exception, we flush the pipeline, copy the architectural register file into the front-end register file. So that's the beauty of having two register files. Front-end register file is used for renaming. Backend or architectural register file, Intel calls it the retirement register file, is used only for updating the architectural state in order when the oldest instruction finishes execution, okay? And whenever there's an exception, you need to synchronize the architectural register file with the front-end register file. Front-end register file is speculative because lots of instructions are in the machine, but you're flushing the machine. So basically take the architectural content of the register file and put it into the front end. So it's a basic simple copy, plus the flush of the machine, of course, right? Okay, so basically, this is our initial out-of-order machine. We did not have a reorder buffer. We're going to add a front-end register file used for renaming, and then reorder buffer, just like we did yesterday, and an architectural register file. You can see that the front-end register file has valid bits and values. Architectural register file doesn't have any valid bits because it's always valid. Everything over there is always valid. It's just updated when the program finishes or retires instructions. Does that make sense? Okay, so this is really the out-of-order machine with precise exceptions. You need to have reservation stations for scheduling. You need to have a front-end register file for renaming. You need to have a reorder buffer to update the architectural register state in program order. And you need to have an architectural register file to keep the architectural register values. Again, to make sure that we're on the same page, architectural register file is architectural state. It's updated when an oldest instruction retires. Front-end register file is the front-end state, the state that is seen by decoded instructions. When an instruction is decoded, it's renamed using the front-end register file because there are lots of instructions in the machine that are potentially updating the registers, right? Architectural register state is what's visible to the programmer. The programmer can inspect this one, but they cannot inspect this one, okay? Okay, so that's basically this picture in a lower level detail, if you will. And that's the camel that I like showing you. Okay, so there are many, many interesting questions over here. You can optimize this a lot, but one question that's actually very bothersome is, there's value replication all over the place. So these are values. So you have values in the front-end register file. You have values in the architectural register file. Values get replicated into the reservation stations, as you can see. Whenever you actually rename an instruction, you copy the value, tag, and value into the reservation station or some other reservation station. And then values also get replicated in the reorder buffer, because you need to take the value that you're producing and put it into the reorder buffer so that you can later put it into the architectural file. So if the sizes of these structures are relatively large, this value replication can be huge, actually. So imagine reorder buffers on the order of 1,000, let's say. Today, we're marching towards there. Imagine reservation stations on the order of 1,000 also. So 2,000 times 64-bit values. So in some cases, 2 of these values, as you can see, right? So 64-bit values are actually quite large. So there's actually a huge amount of value replication. And imagine a worst case where every instruction is sourcing and writing to register 3. So that's actually basically the same register, well, maybe not writing, to every instruction sourcing register 3, let's say. That's the same register 3 replicated all over the place, right? If no one's writing to register 3, but everybody's sourcing register 3, they're all replicated over here, right? So basically, you're kind of wasting the values. So people have found out a solution to this by consolidating the values in a physical register file. They can centralize the value storage. And everything else can hold pointers. So for example, the front-end register file, not file anymore, it doesn't have values. Front-end register map has the rename registers. This is how you rename the registers, and pointers to the physical register file. Register 1 points to physical register file 18. That's the latest definition of register 1 that you can get from an instruction that's in the pipeline. Register 10 points to physical register file 4, for example. Okay? And the value is only here, basically. That's true for the architectural register map also. Here, architecturally, register 1 is stored in physical register 12. That's the architectural state of the machine. Architecturally, register 7 is stored in physical register 11, etc. And reorder buffer entry also has pointers. So this is how you can get rid of the values. Values are only in the physical registers that are centralized, and everything else stores pointers to the physical register file. Now, this is also nice because this is your rename space now. Your rename space is the physical register file. You can have a physical register file whose size is 1024, and those are the names you have for renaming the architectural registers too. So a lot of machines work this way today because they don't want to replicate these values all over the place. Because values are expensive for multiple reasons, right? They take up space, but they also consume a lot of power. Each value is 64 bits today, sometimes even larger. And whenever you're broadcasting, the value is huge. Tags are actually much smaller. If you think about a tag, if your namespace, rename space is 1024 registers, the size is only 10 bits. The value is 64 bits. Does it really make sense to broadcast all those values and make the system very energy inefficient, right? Because every broadcast takes energy, power also. This is why this is really important, and people actually get rid of the replicated values. So basically, in the end, this is where we build up to. Modern out-of-order execution with precise exceptions. Most modern processors use the following. They have a reorder buffer to support in-order retirement of instructions. They have a single register file called the physical register file to store all registers, both speculative and architectural registers. Speculative meaning the value is going to be produced by instructions in the pipeline, but they may not be updating the architectural register because there might be an exception, right? And later we'll see branch misprediction. There might be a branch misprediction also, potentially. Integer and free registers are still separate. We've kind of been saying that also. There are 2 register maps that store pointers to the physical register file, just like I described. There's a front-end register map. That's also called a future register map. That's used for renaming. It's called for future because it's not really the architectural state that's updated. It's future instructions are coming and renamed using that. That's also called rename register map. And then there's an architectural register map that's used for maintaining architectural or precise state. And this design avoids value replication in reservation stations, reorder buffer, etc. And that's basically the design that we have seen over here. So how does this actually impact the reservation stations? So let's say I didn't show you the reservation stations over here, but the reservation stations also don't have values anymore. And if you look at this, this is the reservation station for add unit, multiply unit. You have the value and the physical register ID, which means that you need to access the physical register file before you access the functional unit, actually. Because what happens is, whenever someone broadcasts a tag, they update the physical register file. They don't, with the value. They don't update the value over here because there's no storage of value over here. Okay? We've just moved the value storage to the physical register file. Before an instruction gets dispatched to its function unit, it needs to read the value from the register file. So this is how the pipeline changes. At decode or rename, we allocate the destination physical register to a destination architectural register. Again, at decode and rename, we read and update the front-end register map, okay, just like we did earlier. And then we wait, we put the instruction into the reservation station. It waits until both of its sources become valid. Before execution, the instruction accesses the physical register file to get its source values. And then after execution, it accesses the physical register file to write its result values. It still broadcasts the destination physical register as a tag. So, but the value doesn't get broadcast. Value just gets supplied to the physical register file. It doesn't get broadcast. What gets broadcast is the destination physical register tag, which is much smaller, as we discussed, right? Even if you have 2048 registers, that's only 20 bits. Getting to 64 bits is huge, right? You need to have 264 registers, which is very difficult to have if you know that number. Okay, so at retirement, we update the architectural register map with the destination physical register if the instruction is oldest and it didn't cause any exceptions. Okay, and this is a modern processor. Basically, Pentium 3 was like what we discussed yesterday, NetBurst or Pentium 4 in Intel. Essentially is what we described, right? This is the front-end register map, front-end RAT, as they call it. It points to some registers in the physical register file. And this is the retirement RAT, or architectural or backend register file. It points to some other physical registers. They may be the same if the architectural register did not get renamed with an instruction that's producing a new value of that register, right? So this is essentially the same picture that I showed you over here. Yeah, this picture, except in a different way. And they have a reorder buffer, of course, to keep the status and do the reordering. Does that make sense? So this is actually, well, this was Intel Pentium Pro. So there was value replication in Intel Pentium Pro, but that replication got eliminated in the Intel Pentium 4. And most modern processors are like this. Let me quickly go over some things and then we're going to conclude. But basically, these are the major concepts in out-of-order execution. We link the consumer of a value to the producer using register renaming. This associates a tag with each data value. We buffer the instructions until they're ready. This requires inserting instructions into the reservation stations after renaming. Inside the reservation stations, we keep track of the readiness of source values of an instruction, which means that instructions broadcast the tag when the value is produced, and instructions that are waiting in the reservation station compare their source tags to the broadcast tag. If there's a match, source value becomes ready. And when all source values of an instruction are ready, you dispatch the instruction to the functional unit. This means you wake up and select and schedule the instruction. So I think we've kind of summarized these concepts. These are nice. I'm going to start with the later slides, but I'm going to cover some things before I actually cover these slides. I'm going to cover these next time. I'm going to ask you these questions later. But let me actually show you some real designs. So real designs are actually like this. If you go through these designs, these are the reservation stations. You can figure out these are the memory reservation stations, memory schedulers, etc. And there's a register file. As you can see, after you get scheduled, you access the register file. This is Intel Pentium 4. And then you go to the functional units. You can see how many functional units there are, right? Even in something that's 22 years ago, you get a bunch of functional units, as you can see. So this part of the machine is actually quite complex. They don't show everything. This is my simplified version of it from my own paper. This is Alpha 21-264. If you're interested in reading, you can actually read the paper that describes how this operates. It's a bit cleaner, more cleanly explained. This has four integer execution units over here, but essentially reservation stations over here. And then you access the register file after the reservation stations. MIPS was designed such that you never do something like this in hardware. Remember, MIPS is called microprocessor without interlocking pipeline stages. They didn't even want to detect dependencies. Compiler should detect the dependencies. But you can see a modern MIPS, 1996, about 15 years after it was really introduced first time, it's using out-of-order execution. Because they quickly figured out, no way we're going to get the same performance. If you want to compete, we got to do out-of-order execution like everyone else. So that's why this concept is very powerful. This is IBM Power 4, which is one of the first multi-core machines. It used out-of-order execution. Again, you can read these slides. They're not that important, but it basically has 100 instruction windows. I'm going to mention this soon. IBM Power 5 is similar. This is AMZ Zen 2, more recent. It has much bigger windows. And I'll conclude with this slide. This is, again, these are not official AMD or official Apple things, but people, enthusiasts, go and benchmark these machines, and they try to reverse engineer what is going on in the machine. And according to the reverse engineering of some people, over here, you can read them on Untick, you can see that they guess that the reorder buffer on this machine is about 630 instructions, and the integer physical register file is about 350, and FP physical register file is 380. Again, this is there. You can see that the load and store are much smaller, 150 or so, because this is actually the most complicated part of the machine. But you can also see how many instruction execution units there are, right? We had a toy example where we had a multiplier and an adder, but you can see this machine easily has more than 15, 20. Okay, that's the end. Basically, for learning more about the even more complex part of the machine, please watch the lecture we're going to premiere and look at the backup slides. You're not going to be responsible for this, but it's really fun to look at it, I would say. With that, have a nice weekend.